Hi, I'm Mike Lee with Team Horizon, and this is a Team Tech Tip. In this Team Tech Tip video, we're going to figure out how much power your radio system and other components of the aircraft may be using with this great little tool called the Hangar 9 Servo and Receiver Current Meter. This is for you guys who are wondering just how much battery should I use to properly power my onboard system safely during flight. This question has been asked by modelers thousands of times over many decades just because having enough power to complete a flight has always been so critical. Even in the days when the state-of-the-art was a vacuum tube transmitter, pilots had to know how much battery power is available from their battery pack. Finding out the hard way generally meant a flyaway or the destruction of the aircraft as gravity eventually pulled the plane down to Earth. Just knowing how much battery power is available from the battery is only half the formula. The other half is knowing how much power is needed to operate the radio system. This is measured in milliamps. With the Servo and Receiver power meter, current meter, you can also examine most of the electronics and electrical components within the aircraft to get an idea of the power requirements and also track down things that may be causing the system to draw excessive power due to being jammed, improperly installed, broken, or even failed. Let's look at some common system components to see how this works. The best thing about the Servo and Receiver current meter is that it has a common use servo connectors that plug right into the existing servo plugs of the radio system. To use the meter, you simply unplug the component or servo from the receiver, plug it into the meter, and then plug the meter into the receiver where the servo used to be. The meter is powered by the power source and needs no battery of its own. It will read power consumption immediately and will show you the battery voltage as well as the amperage being pulled by the servo or component. Now that you know how it works, let's look at the power consumption of some items in the plane. Let's start with this plane. It's an E-Flight Hawker Hurricane ARF with retractable landing gear and flaps. I always worry about the retract sucking up power from the battery because they need a lot of power to raise or lower the gear. Add to that the need to fully lock into place in order to prevent the gear failure on landing. Let's check it out. Okay, our next test has to do with the servos, how much power they're drawing at idle, and what happens when you have a servo that's buzzing, such as one that's on a control surface that's too tight for it to move and precisely get back to neutral. So we have a servo in that position right now, and it's making a slight buzzing noise, and you can see on the meter it's drawing 120 milliamps. Now I'm going to add a little bit of finger pressure just to see what the effect is on that servo. Here we go. Just a little bit of pressure, and you see it jump from 120 to 140. And add just a hair more, and we can make it jump right on up. 150. Not that much pressure I'm putting on it, but you can see how the difference in that pressure makes the amp draw on that servo. Now let's see what happens on the voltage. Actually, the voltage shouldn't vary very much because of the fact that we're coming off a BEC, which holds the voltage steady from the main battery. But we'll switch it on over anyway. Okay, we're now on volts. 5.53. Let's see what happens when we put that pressure on the servo again. A lot of pressure being put on, and it's holding pretty steady. So the BEC is doing its job. But do watch those connections between a servo and a flight control surface and make sure they're not stalling the servo and drawing excessive amps. Pretty interesting, huh? Okay, so now let's look and see what happens on the amp draw when everything is running, including the motor. We're going to switch to amps. We're going to bring the motor on up and start stirring the sticks. Here we go. Motor's coming up. Amp draw still pretty good. Stirring the sticks. Still about 480 milliamps. Let's go to volts. Still 5.52. Let's stir the stick. Now we're getting a dip there. 5.44. But that's about the same as we had before. And that tells you the BEC is really doing a great job of holding that voltage steady all the way through the range. And our motor's not pulling down the ESC so much to cause a brownout. So we're pretty safe with this motor, pretty safe with this aircraft. I'm very happy with the installation. I think we're good to go. We're now switched back to the voltage side over here, and we're going to stir the sticks a little bit to see how that affects the voltage hold. If the voltage hold is good, meaning the electronic speed controller and his BEC is putting out a good steady amount of power, then we're in good shape. Here we go. We're going to start stirring the sticks right about now. That's a pretty good test. It dropped down to 5.45, which is only 1/10 of a volt. And that tells us that the BEC is doing a really good job of holding that voltage steady for us. And there was no hesitation at all, so that's a good test. Let's see how many amps we can draw while stirring the sticks here. Switch on over to amps, and here we go. Now look at that draw. It jumped up to 390 milliamps, 400 milliamps. Now, of course, we don't fly that way stirring the sticks all the time, but it tells you a worst case situation if you did fly that way. Maybe in a panic situation trying to pull out of a dive. You can see what kind of stress is going on that battery and how much power you're using up. If you use up power at that kind of rate all the time, you won't be able to have much more than one flight per day per battery. But it's a great test. Good to see how it works. Now let's add a little bit of power from the motor. Let's see what kind of amp draw we get. Holding steady. So as you can see again, the BEC is doing a fantastic job of getting power to the servos. There was no brownout. The motor was running. It should have taken a lot of power off that, but everything worked just fine. This is a great test. The airplane's set up very nicely. In this test, we are looking to see what kind of amp draw occurs when deploying the retractable landing gear and what effect on voltage it is, with and without the motor running. This will help us know how much power might be used by the retracts and if this amount of draw might ever cause a brownout on the receiver. For this test, we'll use a battery that is half depleted, and it's very rare to experience a brownout using a fully charged battery and far more likely to occur much later in the flight. We'll also be running the motor as this would simulate the actual flight mode other than being in the air itself. So here we're now looking at the meter in the amperage side of the meter. And we're pulling right now about 110 milliamps. And the retracts are ready to go. So here we go. Watch the meter as we retract the gear. They're in the up position. Retracts down. Retracts up. 450 milliamps on the way up. Retracts down. 490 milliamps on the way down. Retracts up. So we're looking at between 450 milliamps and 500 milliamps, 490. And that's a pretty heavy draw. The good thing is that it's only occurring for a period of 2 seconds at a time, which is okay. Let's see what happens on the voltage side. We're going to switch our meter to volts. Right now we're drawing a steady 5.54 volts right now. And here we go with the retracts. As they're in the up position, retracts down. Retracts up. So in the worst case we just saw, retracts down, retracts up. We're using about 1/10 of a volt, which is really good, and also tells you that the BEC is doing its job of supplying a good steady stream of power to that retracts unit. Now let's do the retracts while we're stirring the sticks. Let's start stirring the sticks, and here we go. Retracts down. Retracts up. Retracts down. Retracts up. And as you saw, at one point it dropped down to 5.5 or 5.35, which is pretty good dip. That's 2/10 of a volt. But we'd never drop down below that point, and that means that the BEC is really doing a great job. Now let's add a little bit of power to it, and we're going to go into the amp mode to see how many amps we're pulling while stirring the sticks and the motor running. Motor's coming up. Stirring the sticks and running the retracts. Here we go. Retracts. Up. Retracts. Up. Now you saw where there was some serious draw in there. Everything being stirred around, including the retracts going up and down. And we saw a draw at one point of over 700 milliamps. So that tells you just how much power this thing is drawing. And yes, there is a possibility of a brownout if you were to go much higher than that. But we don't fly with stirring the sticks, and we don't fly stirring the sticks and putting the retracts down. We're usually pretty sedate. So that's the worst case situation that would be occurring if we had that kind of draw. And if you were using a separate battery pack, you'd have to run a pretty steady sized battery pack in order to keep that kind of load going. So now you've seen how the servo and receiver current meter works for you. Knowing what the normal current draw is, and then performing periodic testing may tell you that something could be causing a servo to stall and suck up battery power, or worse yet, a possible servo failure. This is also a great tool to use for ensuring that your servo setup is correctly done. We do have another tech tip video that uses the current meter to perform servo balancing. Check it out if you want to know more about how this tool can help you out. I hope this video has been of assistance to you and helped you enjoy your hobby even more. Stay tuned for more tips, tricks, and techniques from the team. I'm Mike Lee for Team Horizon, and you just got a Team Tech Tip. Thanks for joining us.